Hello and welcome to another episode of Math-Adda with your host Shankadev. So, in the last episode, which was about that circle problem, one man hopping on a circle, I mentioned that I'm going to do some kind of a generalization of that problem. So, actually, it's not really a generalization, but I'm going to use that problem, the stuff we derived in that problem, to solve a problem in a higher dimension. That means the previous video is a prerequisite for this video, and there is another video that you need to look at, which is the video on creating new spaces. So I'm going to leave the links to these two videos in the description.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances.
Let's start. You probably remember that you can construct a torus starting from a square. How? So it was a quotient space construction. It went like this. So we started with the space R2. Then we said, look, the points A comma B and C comma D are related if and only if A minus C is an integer and B minus D is also an integer. Then we tried to develop a model for the space. And the way we did it is the following. We said, look, any point x comma y is equivalent to the fractional part of x comma the fractional part of y. Therefore, any equivalence class has a representative in the square 0 comma 1 cross 0 comma 1. Now I did it like this. So suppose this is a square. Then note that x comma 1 is equivalent to x comma 0, which means the blue sides are actually equivalent, so they should be joined. Moreover, 1 comma y is equivalent to 0 comma y, which again means the yellow sides are equivalent, so they should be joined as well. We do this process in two steps. First, we do it like this. We bring the two blue sides together, and that gives us a cylinder. And then we bring the two ends together, which are the yellow sides now. And that finally gives us a torus. I'm going to revisit this construction to say something else about this problem. Now, you can, instead of looking at just one square, you can look at all the squares. I will make it clear what I mean by this. Suppose this is R2, and you have a bunch of squares. The vertices of these squares are the points with integer coordinates. So you have probably seen this before, because this is what basically the graph paper is. Okay. Now, such a structure, such an arrangement of squares or other polygons is called a lattice. And the points that are at the vertices of the lattice are called lattice points. So what I was going to say is, if you do something on R2, that is going to have a representation in T2, because T2 is the torus. It's because the whole plane R2 is in some sense projected to T2. I will tell you what I mean. Suppose you have a line like this. A line that goes on and on. So you cannot consider the whole plane, because the way we construct the torus is by restricting to a square and identifying. So what's happening is, the line is starting at this point, it's going to this point, then it is going out of the square, and we do not know how to deal with it because we identify just one square, we don't care about the others. So what we do is, we know that this point is actually identified with this one. So at the level of the torus, those 2 points are the same. So instead of going further from here, I identify this point with this point, and I go further from here. Now what happens is, again, I have hit a boundary, and it's hard to go, like we cannot go past the boundary, but we can do something else. This point on the boundary is identified with another point on the other side. So instead of following this line, I can follow this line starting from the other side, and on, like that. So we had a line which spanned the whole plane, and now we reduced it to something which is actually contained inside the square, and thus contained in the torus. You can say it in some other way actually. So the line is a subset of R2, right? What we are doing is actually, not belongs to, it's a subset. The line is a set of points which is actually a subset of R2. So what we're doing is, we're taking each point on the line, and we are finding another point in the square which is equivalent to that point, and we are like reducing the whole set into something smaller. Okay, so we are looking at the points on the line not as points but equivalence classes. Now I can ask you, given some line which passes through the origin in this case, so we're restricting ourselves to the case when the line passes through the origin, I can ask, so what is the image of a given line on R2 on the torus? The answer is going to depend on the line actually. So suppose we have the line y is equal to x. What does it do? It starts here at one vertex and it goes to the other vertex. Now this final vertex is identified again with this point. So it just keeps going on and on between the same thing. Okay, like that. So when you transform this to to a torus, what is it going to give? It's going to give you it is going to give you a circle actually. So let's do it like this. I think it would be better to use another color. So it started from one point here and it ended on another point there. And when we join them together, it's just going to be a curve that crosses the whole thing. So it's kind of a curve that crosses the whole thing. And you can do more actually. So suppose you have y equal to 2x. What does it do? It starts from 0, 0. Now, when x is equal to 1, y is supposed to be equal to 2. So it is supposed to go like this. But we are not going to allow it to do that because it's getting outside the square we like. So what we do is we get it back here and then allow it to continue. But the thing is, after that time, it's actually reaching one of the ends, 1, 1, and 1, 1 is the same as 0, 0. So what happens is it comes back to 0, 0 and then repeats. So what will happen is it'll go like this, then come to this point, then go like this, then again come back to 0, 0 like that. So it is going to be on the torus, it is going to be a curve that wraps twice. Again, we can try to visualize that. So it goes like this. Like that. So it's going to be a curve that wraps twice around the torus. In fact, you can check that if you take any rational slope, so if you take any y equal to some rational number times x, then this same phenomenon happens. So it actually wraps around the torus a number of times, then comes back to the same point. Now the question that I'm going to ask is, what happens? What happens if you take the line L equal to x comma alpha x, where alpha is an irrational number? The answer is not very simple. Before we give you the answer, we would like to claim something. So what happens is, when alpha is irrational, the thing spins very quickly. So it makes many, infinitely many terms, and it does not ever come back. In fact, if you take the torus and from a distance you look at the image of the line on the torus, it will look like the whole torus. So it will just look like a torus made up of where. I don't know if it's easy to imagine or not. So what's happening is the curve is actually filling up the torus. Such a curve is sometimes it's called a space filling curve. Mathematically speaking, what's happening is, it's given any point on the torus, you can find a point on the curve which is arbitrarily close to that. So any point on the torus can be approximated by points on the curve. That should serve to give you a better idea of what's going on. So it's becoming a very dense coiling process, as if the whole torus was just the curve, where it's just the curve, nothing else. We'll have to make this statement precise now. Oh, sorry. As you probably remember, that the equivalence class of a point is denoted by some point, the point and a third bracket. So given any xy on R2, what is the image of xy on the torus? It is let's write it in that way. Its representative on the torus is fractional part of x, comma, fractional part of y. Claim there exists some x, and we have some epsilon greater than 0, which can be as small as you want. It's a positive, very small number. So claim is there exists some x epsilon real, such that the distance between the points xy, I mean the fractional parts, and fractional part of x epsilon, comma, fractional part of alpha x epsilon is smaller than epsilon. So what's happening is the line on the R2 is very, it's very thin, right? It's just one strip. But when you restrict it to the torus, it's actually very dense. 2 points on R2 can be very far away, but when you bring them to the torus, they can be very close by. That's what this claims. It means that given any point on the torus, you can find a point on the line whose representative is close to that point on the torus. So I think to make our life easier, we can start by assuming that x epsilon is actually equal to x. Then it reduces to showing that it is possible to I think what we should assume, x epsilon fractional part is fractional part of x. We need to show that. We show it is possible to find some, say, x naught in the equivalence class of x epsilon, such that alpha x naught fractional part is close to y fractional part. Now we can define xn to be n plus fractional part of x, which actually gives us xn fractional part is equal to x fractional part. So we are going to prove that there exists n such that the distance between fractional part of y minus the fractional part of alpha times n plus fractional part of x is less than epsilon. But now we are actually in familiar territory. Why? Alpha n. So this thing here, alpha times n plus alpha times fractional part of x. This is the kind of thing that we have seen in the previous problem, the one with the person hopping on the circle. So this is the initial point. In that problem, the initial point was 0, but here the initial point is something different, which is alpha times the fractional part of x. And alpha n is the step we are taking. Alpha is the step we are taking. So our positions are going to be alpha fractional part of x plus 2 alpha plus alpha times fractional part of s, 3 alpha, like that. Now we have reduced this problem to that problem, and we have solved that problem. We know that these numbers, as n varies, these numbers are dense on 0, 1. We have proved it in that problem. In particular, given any y between 0 and 1, we have some member of this set, of this orbit, if I may use the terminology that I introduced in the previous video. There is some member in that orbit such that the difference alpha n plus alpha x fractional part minus this is less than epsilon. So here you have it. It's a kind of generalization of that problem. The precise statement is that if you take a line with irrational slope on R2 and you reduce it to a line on the torus using this identification that constructs from R2 the quotient space, the torus. So under that identification, which is also called a projection sometimes, that line with the irrational slope actually becomes a very coiling thing. It coils around the torus many times. It's not a closed curve because it never passes through the same point twice. And given any point on the torus, you can approximate it by the points on the cube, the points on the curve. Okay? So that's it for today. Please share your thoughts on in the comments, and please like, share, and subscribe. Bye-bye. See you next time.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.